So one issue is that Zico talked about the polls last time, and he mentioned that we're going to check participation based on the polls, and there's going to be some threshold that, of the fraction of problems you have to get right in order to get the participation grade. So we've decided to set that threshold to 0, which means we don't care if you get the questions right or not. Okay, so really the polls will be used to just keep track, whether you're in class. But it's really important to us that you won't feel nervous, about getting the polls right. So really the goal is to just have everybody participate, have everybody engaged, and not worry about, whether it's right or wrong. In particular, I often include an option for beats me in the polls. So don't be afraid to even choose that option. That actually helps me to see if people are following the material or not. Okay, so if I see many people choose beats me, then maybe we have to repeat like the last part of the lecture. A second announcement is regarding office hours. So Zico and I are trying this time to do office hours by appointment. And for me, the main reason is I feel that sometimes office hours are not very effective because if they're happen to be before the homework is due, there are many people sort of parked outside the door and end up waiting a long time. If it's not before homework is due, often very few people show up. So what we'll try to do is have the TAs have fixed office hours in the sort of traditional way, whereas Zico and I will have office hours by appointment. We're very responsive, so if you email us, we should be able to set up an appointment pretty soon. And we're going to try that. If we see that too many people want an appointment or too few people, we may switch to regular office hours, but we'll try this for now. Okay, so we're going to talk today about search. And by way of introduction, let me just mention that search is not necessarily one of the areas of greatest expertise for Zico and me. We said this course will mostly focus on things that we are really experts on. This is a bit different because it's just a topic that fits really well with the first part of the course that's about optimization. It's a core topic in AI. So we've decided to include this topic as well. We'll devote 2 lectures to search, and we'll see how that fits as we dig in deeply into optimization in the lectures after that. I guess many of you have seen search before, so we'll talk about A star and some variants of A star in these 2 lectures. I guess this will not be new to many of you, will probably be new to some of you. So hopefully we'll dig in a bit deeper than what you've seen in the past. But also this will be relatively fast. Okay, so for those of you who haven't seen this before, there will be maybe small gaps that you'll be, that we hope you'll be able to fill on your own. Cool, so let's just start from the very basics, talking about what a search problem is, the basic formalism, and then talking about how we solve search problems on a high level. So a search problem has a set of states, also known as configurations, a start state and goal states. So there's some initial states, and there are maybe multiple states designated as goals. We're trying to reach one of the goals. And we also have a successor function that basically tells us which states are reachable from a given state and how much making that move costs. Okay, so it's a function that maps a state into a triple of action, state, and cost. So we basically have possible actions we can take, which states are going to take us to, and how much taking that action costs, how much this transition costs. So let's see a few simple examples. This is sort of an example that's popular in CMU. For those of you, probably very few of you, but if you happen to be undergrads here, there's this course 251, which I teach, Great Theoretical Ideas in Computer Science. And the first lecture basically uses this pancake sorting example, because it's just a really nice domain to teach what upper bounds and lower bounds are. But this, one nice anecdote about this problem is it was introduced in a paper by Bill Gates and Christos Papadimitriou. The problem is defined as follows. We have a bunch of pancakes of different sizes. And initially, there's some stack, and they're not sorted by size. Our goal is to get to a state where they're sorted by size from the smallest to the largest. Now, the actions here are pretty weird. So we have the spatula, which we can insert in any place in the stack, and then flip that whole prefix of the stack upside down. So from this state, we can either insert our spatula here and flip the first two pancakes, or here and flip the first three, which is this, or at the bottom and then flip the entire stack, which gives us this state. Okay, so we have three possible actions, and then you can see the transitions for each one, which states we get. And here the cost of every action is 1. Okay, so every place we insert would cost us the same. And then you can draw this graph of states, and then with outgoing edges into the states that are reachable from that state. And ultimately, so I've only drawn a small subset of the states, but I just highlighted the fact that there's a specific goal state here where the pancakes are sorted. That's just a very simple search problem. Here's another simple one, which is what you have in homework 0. So this is the 8 puzzle problem. So here we have a starting state, an initial state, where the tiles are just laid out in some way on this 3x3 board. And the rules of the game is we have a blank tile at each point, and we can slide the tile into the blank spot. So for example, from this state, we can either move 3 here or 2 here. These are the two possible moves. So if we move 2, we get this state. If we move 3, we get this state. Right, so again, we can draw this graph that tells us where the vertices are states, and the arrows give us the transitions, the possible actions we can take. And again, the cost of every action is 1. And the goal state is the specific state where the numbers are sorted from 1 to 8. Okay? So that's another simple problem where every action has the same cost. And actually, in both of these examples, we had only one goal state. So here's a third quick example, and we'll talk more about this kind of stuff in the next lecture. So this is a map of Romania. This is actually something that's pretty interesting. If you look at the Russell and Norvig book, you'll see that all of the examples use this map of Romania, all of the examples of A*. And this has been caused big trouble for generations of AI teachers who have tried to pronounce all of these city names and have broken their teeth. And I actually did that mistake first time I taught AI at CMU. And then I learned my lesson, so I'm just giving this map for this particular example. But when we actually do examples with graphs and try to run algorithms, we'll just do abstract graphs and not this crazy Romania map. But the idea here is, you're trying to get from Arad to Bucharest. This city, I still don't know how to pronounce its name. But then you have roads that you can take. And the numbers, the cost of taking a road is basically the distance, of traveling this road between the two cities. And then, you can just think of it as a search problem, again, where the states are the cities, and an action we can take as a road that we take, and we have the cost that is based on the length of the road. And here the goal state is Bucharest. Okay, so, that's sort of the overall formalism for how we think about search problems. Now let's talk on a very abstract level about how we solve search problems. So there are two algorithms. The more basic one is called tree search. And this is sort of very high-level pseudocode, but let's talk about the main idea. So, we start with a set of frontier nodes that only contains the starting state. So we think of frontier nodes as nodes that we have discovered, but we still need to explore. Now, the loop does the following things. If there are no frontier nodes, then we return failure. That means we haven't found a goal yet, and there's nothing left to explore, so then we haven't been able to find the goal. If that didn't happen, if we have frontier nodes, we choose some frontier node for expansion using strategy. And we'll talk a lot more about strategy in the next 20 minutes. But for now, let's just leave it at that. We have some strategy for choosing which frontier node to expand. If the node contains the goal, then we return the corresponding solution. And here, this is one of the places where I'm skipping details that I think are relatively obvious. But the idea is that we would keep pointers that tell us, which was the predecessor of each state in this exploration path that we took. And then when we say return the corresponding solution, you kept track of all of the pointers and that gives you can use these pointers to recover the full path to the solution, to the goal. So if the node does not contain a goal, we expand the node, so we see which nodes are reachable from that node, which actions we can take, and which nodes or which states we reach. And we add the resulting nodes to the set of frontier nodes. So now we've discovered a bunch of new nodes, and we will be able to explore them in the future. So this is tree search, and again, we'll talk about this, instantiate the strategy and talk about this in more detail. But let me just point to one sort of high-level issue with this, is that it can expand many nodes corresponding to the same state. So we can basically explore the same states again and again and again. Okay? That pseudocode didn't keep track of which states we've already discovered and expanded. So just to see how big of a role this can play and how complex things are, if you think of our tree search thing as basically a search tree, right, where every time we think of, we reach some node, we expand it, and then its predecessors on the next level are the states reachable from that node. So you can think of this as this search tree. Now, if we think specifically of our search problem as being represented by this 2D grid, starting from this state, so from here we would discover these 4 states. Now, each one of them on the next level, when we expand it, we again discover 4 states. Even in the next step, it would be the initial state would be discovered again, would again be added to the frontier. And notice that this state would be added by both this state, and so on. So we're doing a lot of double work. And in particular, if we think of this tree, because the branching factor is 4, at depth d, so basically d moves from the initial state, it would have 4 to the d leaves. In contrast, think of how many nodes or how many states we actually have at distance d from the starting states in a grid. Right? So I claim that this is 4d. Let's just check it for d equals 1 and 2. So for d equals 1, we have 4. Right? And for d equals 2, we have 1, 2, 3, 4, 5, 6, 7, 8. And it's very easy to prove by induction that it's actually 4D. So, so basically the amount of extra work that we're doing is exponential. Right? Instead of something that's linear in D, we're doing something that's exponential in D. So this is pretty bad. Now, one way to address this, just a few words of wisdom from Bender. So Bender is going to be my sort of mascot for the course. He's a robot, obviously, from Futurama, and from time to time he'll have some smart things to say. So here his words of wisdom is algorithms that forget their history are doomed to repeat it, and that's what we want to prevent, sort of preventing the algorithm from forgetting the history. So the idea would be to switch to graph search, which is a very similar algorithm, but keeps track of the work that it's already done. Okay, so let's just look at the differences in the algorithm. So, the initialization is the same as before. We have the set of frontier nodes that contains the initial state. Now, in this if, before we said if there are no frontier nodes, now we're saying if there are no unexplored frontier nodes. I've added the new stuff in green. Okay, so now we just look at unexpanded frontier nodes. If we have already expanded all of the frontier nodes, then we return failure. Okay, so now the idea is we're not going to expand a state that was already expanded in some node. If we still have unexpanded frontier nodes, we choose an unexpanded frontier node for expansion using the mysterious strategy, and we add it to the expanded set. Okay, so we expand it, but we also remember that this was expanded. So we won't have to do the same work again. Like before, if the node contains a goal, we return the corresponding solution by keeping track of pointers. Else, we expand the node and add the resulting nodes to the set of frontier nodes only if they're not already in the expanded set. Okay, so again, if we expanded them, we're done with them and we can forget about them, but we do add them to the frontier if they haven't been expanded. So this is graph search. In homework 0, we're asking you to implement the graph search version of A star, which we'll get to in a few minutes. For now, I actually want to focus on tree search. Okay, so for most of the lecture, I'll talk about tree search. In the last few slides, we're going to switch to graph search. Okay, but for now, we're going to think about this very simple version where we don't even keep track of which states we visited, and we can do the same work over and over. And we'll see that this actually has an advantage in terms of getting optimality in some cases. Cool, so let me just mention, there's this terminology of uninformed versus informed search. So in undergrad AI classes, for those of you who have taken one, usually there's a full lecture about uninformed search. So these are algorithms like BFS, DFS, bidirectional search, iterative deepening, DFS, and so on. So the idea is that these are algorithms that can only generate successors and distinguish goals from known goals. That's all they're allowed to do. So for example, under breadth-first search, you have some strategy for generating successors. You sort of look at the distance from the initial state and you expand according to that. But that's basically all you know. And when you reach a goal, then you're happy and you're done. Informed search are algorithms that make use of some heuristic that basically tell them whether one known goal state is more promising than another. So it gives them additional information that they can use in order to decide which node to explore next. So I'm just going to give you one example of an uninformed search algorithm, and then we'll talk about informed search for the rest of the lecture. Okay, so this algorithm is called, very confusingly called, uniform cost search. Yeah, so let's talk about the algorithm, and then I'll tell you why I think it's called uniform cost search. But it's really a very bad name. This is basically the generalization of breadth-first search to the case where we have different costs on edges. Okay? So the idea is we're going to denote by G. G is a work function, and G of X for a node X is going to be the work done so far in order to get to the node X. And what we'll do is our strategy will be to expand the node that has the lowest value of G, where we had to do the most little work so far. And notice that if all of the costs are 1, then this is basically going to be the number of edges that we have traversed, which will coincide with breadth-first search. For those of, I'm sure everybody knows what BFS is. Okay, so let's see how uniform cost search works on this example. And I'm not doing the map of Romania, just this very simple graph. So initially, and what I'm doing is running tree search with a strategy instantiated to uniform cost search, right? So I'm starting with the initial state S, and we have G equals 0. We haven't done any work so far. So now from S, I'm expanding S. I'm going to discover A with a total work done of 1, right? Because the weight of this edge is 1. So now I have only one node on my frontier A. I'm going to expand it, to choose it and expand it. And now I'm going to discover B with a total cost of 2, D with a total cost of 4, and E with a total cost of 6. Okay, so now I look at the G values, and I see that the lowest one is B. Right, so my strategy tells me expand B next. So expand B, and then I find C with a total cost of 3. Cool. Now I'm looking at my G values. The lowest one is C. I choose it for expansion, but it doesn't have any successors. So I'm done with that. Now I look at my frontier again. The next one, according to G value, is D. So I go to D, and I expand it. And now I discover T with a total G value of 6. Right? 1 plus 3 plus 2. Now I have a tie between E and T, so let's be bad for ourselves and expand E first. So I expand E, and what happens? I discover D again, this time with a G value of 7. Right? So this is a node I've already expanded, but now I'm doing tree search. I discovered it again through a different path, and now the G value is 7. This is, by the way, a slightly subtle point that maybe I should emphasize. So there is a distinction between states and nodes in this tree. Right? The states here are these. But what happened here is the state D actually appears in multiple nodes. And these nodes have different pointers and different path that was used to get to that node. Okay, so there is a distinction between state of the search problem and the node in our search tree. which is associated with the state, but also with the path that was used to get to that state. Cool, so at this point my frontier is this, the lowest G value is T, I expand it and I'm done by the tree search algorithm that said once you expand the goal state then you're done. And now I just, I kept track of the pointers, so basically when I look at my solution I see that my path was from S to A to D to T. Okay, and very importantly it was from this D and not from this D. Cool, so that's uniform cost search. Why is it called that? Like I said, it's a really bad name because the costs here are not uniform. So apparently some people thought that it makes sense because if you're in a very large graph where cost can change significantly over time, at any point in time you're exploring nodes that have more or less the same cost. Okay, so that's a source of the name, but I do think it's very confusing. Cool, so that's all I wanted to say about uninformed search, and I think this is stuff that probably BFS, DFS, probably almost all of you, if not all of you, have seen before. So let's talk about informed search, and specifically, we'll find our way pretty quickly to the A-star algorithm. So like I said, informed search really relies on having some heuristic function, okay, which gives the algorithm additional information about which states are more promising. So here's an example heuristic for the map of Romania. This is the last time we'll do the map of Romania. So, like before, we have like the length of different roads. But as a heuristic, we can use this table that gives us the aerial distance between our starting point. Is it from a road? From Bucharest, right. So this is the aerial distance from Bucharest to these different cities. Okay, and so we're trying to get to Bucharest. Initially in Arad, we're 366 kilometers away from our goal of Bucharest. But then, this also gives us some information about how promising other things are. And then, when we try to decide which city should we go, we haven't really computed how much work we'll have to do once we reach that city to get to Bucharest. But we have this estimate that says, if the aerial distance is much smaller, it's probably closer to the goal. So that's the heuristic. Okay, so here's, so now we have some heuristic function h for our problem, where h of x gives us this heuristic estimate for how promising h is or how close it is to the goal. So it's basically an estimate for how much more work we'll have to do to get from x to the goal. And let's go back to our example, but now we're going to add these h values as well, so we get additional information. So every node has an h value. And I'm going to run this greedy algorithm, where now my strategy is going to be just expand by h value. Okay, so that's all I care about. The most promising thing will be expanded first. Good, so let's run tree search for this greedy search algorithm, with the heuristic shown in the example. So like before, we start with S, that's the only thing on our frontier. We expand it, we discover A. A has a heuristic value of 5. That's the only thing on the frontier. We expand it. And now we discover B, D, and E, each one with their h value. So the one with the lowest h value is actually E. And also notice that this is something that's stupid about this heuristic, right? Because it's pretty clear by looking at this that D is closer to the goal than E, but somehow E has like a lower heuristic value. Fine. So we expand E next. And then we discover D. Okay, so now on our frontier we have B, this D, and this D. Both of these D have an h value of 2. They're indistinguishable to us. So let's break ties against ourselves in this case and expand the bad D. And now we discover T with an h value of 0. We expand it and we're done. But what was the path that we took in order to get to T? It was from S to A to E to D to T. Right, so this is not the optimal path. The optimal path, of course, is not doing this detour, but just going like this, which is what we did before with uniform cost search. So this just says, greedy search may not be optimal, and it may not be a very good algorithm if we only rely on this h, and h may not be very smart. Yeah.
So there is no consideration of the distance at all. It's only heuristic.
Yeah, so greedy search only looks at the heuristic. And on the very next slide, A star will actually take the distance and the heuristic into account. Okay, so this is exactly what A star is doing. Yeah.
So why did you call the D a bad D? I mean, it's the same D. It's just
Good question. So it's not the same, it's the same state, but not the same node in our search tree. Okay, so what happened was, when we expanded A, we generated a node associated with D, but its predecessor was A. So it was discovered through A. And if we reach T through the first expansion of D, then our path would be this one. So this was one node in our search tree with a pointer to A. Then, when we expanded E, we got another node associated with the state D, but this one had as a predecessor the node E. Okay? And this was the bad D. So now on the frontier, I had the good D that has a pointer to A as the predecessor, and the bad D that has a pointer to E. And now, and the one I expanded was the bad D that had a pointer to E, and I got the bad path.
So if you're at a certain state, are you looking for the smallest heuristic value that is next to it?
When I'm in, the algorithm, when I'm trying to choose which node to expand, let's go back to the tree search algorithm. So what it's doing is, it's saying, when we have frontier nodes, we choose one of them according to strategy. So it doesn't even have to be adjacent to the previous node we expanded. We have the set of frontier nodes. Maybe some of them were discovered in the past, right? Maybe we expanded some node. We added many nodes to our frontier. We expand another one, we added many nodes. But now maybe we'll go back to one of the old ones if they have a better value according to our strategy. Okay, so it's not necessarily something that's adjacent to the last state that we expanded. We just go back to our frontier, look at all states on our frontier, and choose the one that is best according to the strategy, which in our case was the best heuristic function value.
So that's just an example you're giving A to S to E to D to T.
Yes.
It could,
Right, I just wanted to give like an example where it's suboptimal.
where heuristic is any f of x or any value. Heuristic could be based on any function.
The strategy could be based on any function. Right, so this was like a specific strategy that only looks at the heuristic function, and a specific heuristic function that wasn't very good. Okay, good. So let's talk about A star, which sort of tries to fix this. So the idea behind A star is, as was just mentioned, we're worried about just looking at the heuristic. We want to look at the work that we've done so far. So what A star does is simply define the function f of a node to be the sum of the work done so far, plus our estimate of the work that still has to be done to get to the goal. This is very natural. Why is it called A star? Because the people who developed it first had an algorithm called A1, then A2, and then they found an optimal one, and they called it A star. Okay, so here's the first poll of this class for you guys. So we're going back to the same example. And what I'm asking you here is which node is expanded fourth. Okay, so the initial state will be expanded first, and then some node will be expanded second, and third, and fourth. And the question is, which of these nodes will be expanded fourth? D, E, T, or C? So in order to get to this poll, this is poll number 1 on Piazza. I posted it yesterday, so you have to go to Piazza. You'll see like the list of polls, the list of all posts. And then if you look at the stuff from yesterday, you'll see 5 polls. This is poll number 1. So what I'm going to do is I'm going to open the poll. And I'll give you a bit more time on this one because for those of you who have to set it up for the first time. And then I'll tell you when you have 10 seconds left. We'll close the poll. We'll look at what you guys think. And then we'll talk about it. Okay, it's really fun how in the beginning of the course we got like 111 votes. It goes down over time, but it's great that so many of you are here. So here are the results, and this is really great. So 81% of you got it right, like the T will be expanded fourth. Let's just quickly go over this. All right, so what's happening is we first expand. So we expand S, then we get A, we expand A second, we have no choice. And then after we expand A, we get D with an F value of 4 work plus 2 heuristic, that's 6. We get E with 6 plus 1, that's 7. and we get b with 2 plus 6, that's 8. So the smallest among them is d that had an f value of 6. We expand d. Then we get t with a total work of 6 and an h value of 0. So that's again an f value of 6, which again will be the lowest in the frontier, and that will be the next one to be expanded. Okay? Okay, so there was one question about optimality, and what I want to do is spend the next 20 minutes or so, maybe even like most of the lecture, thinking about when A star is optimal. Like, what are the conditions that are needed in order to make sure that we actually find the optimal solution? Yeah.
In the previous problem, don't T and E have the same F value?
I think so E had an F value of 6 plus 1, that's 7. Right? So the total work was 1 plus 5 plus the H value of 1, that's an F value of 7, which is higher than the 6. Okay, so one question just to slowly start thinking about optimality. So one question is, we said that tree search will stop when it expands a goal. So one question is, is this really necessary, or can we stop when we discover a goal, when we add a goal to the frontier? And this is an example showing that we shouldn't stop when we discover a goal. So look at this example. We start by expanding S, and we add both A and B. Now, B is farther away from T. This edge is more expensive than this one, but our heuristic function isn't the best, so it actually gives lower H value to B than A. So the next node that A star will expand is B, and then it discovers T with a total work of 5, okay? But this is not the optimal path. So at this point, T has an F value of 5, A has an F value of 4, 2 plus 2, so the next node to be expanded will be A, and now we're going to again add the state T as a node to our search tree, but this time with a total work of 4, and of course then it will be expanded, and then we're done. Okay? So, yeah.
Sorry, aren't B and A equal, or like 4, when they're discovered?
So when they're discovered, B has an H value of 1, and A has an H value of 2. So our heuristic function is silly. It thinks that B is closer to the goal, even though A is actually closer. Right? And what F is looking at is the total work, which is the same, like you said, plus the H value.
Oh, you're right, yeah. Huh? The edge.
Yeah, exactly. So they are the same in terms of G, but not in terms of H. And H is sort of messing with us here and telling us that B is actually better. Right?
Isn't that a natural byproduct that P will look at Fx plus Hx? We are greedy about that, right?
Yeah, so the only thing I'm saying here is like we should not stop when we discover a goal, we should stop when we expand the goal. Okay, so actually here when we ran our algorithm, it does eventually, like when it expands T, it expands it through the optimal path. Okay, because it didn't stop when it discovered it. So this is fine. I'm just saying like this is necessary for this type of algorithm. Now here's another very interesting issue. So here's an example where A star is not optimal, even though we'll only stop when we expand the goal. Okay, so initially we expand S with an H value of 7. So we discover T with a G value of 5 and the H value of 0. So the F value is 5, and we discover A that is actually on the optimal path, but its H value is very large. It's 6. Okay, so we discover it and we add it with an F value of 7. So what do we have now on the frontier? We have T with an F value of 5, and we have A with an F value of 7. So that means that we're going to expand T next, and then we're done. Right? But we discover T through the suboptimal path that goes from S directly to T. And the reason is that here the H function really messed us up. Right? So here, it was telling us, whoa, like you have so much work to do to get from A to T, 6, even though it's actually much less work. So really what happened here is that our heuristic function was very pessimistic and told us that we need to do a lot more work than we actually need to do. So what we're going to do is we'll circumvent this issue by being optimistic in our heuristic function, and we'll show that this is going to be enough to guarantee that A star is optimal. Okay. Okay, so let's define this formally. So this property of being optimistic is formally called admissibility. It's a property of a heuristic function. We say that H is admissible if for all nodes x, the heuristic value of x, our estimate, is at most H star of x, where H star is the cost of the optimal path from x to the goal. So H star is like the work that we actually have to do to get from x to the goal. H is our estimate. And what this is saying is our estimate is at most the work that we actually have to do. Okay, so this is like a very intuitive definition of being optimistic. We never think the work that we have to do is more than the work that we actually have to do. So for example, if you think about a map and you take the aerial distance heuristic, this is going to be an admissible heuristic, because it's always going to be easier to fly in a straight line compared to traveling on roads that may not take you in the shortest path between 2 points. So this will always underestimate the distance. Another example, a degenerate one, is H, which is identically 0. Okay, this doesn't give you any useful information. If you use this, you'll basically be doing uniform cost search. But it is an admissible heuristic function. It always underestimates the amount of work that needs to be done. Cool. Okay, so what I want to show you is, can you raise your hand if you've already seen this proof that A star is optimal with admissible heuristics? No, so really few of you. That's interesting. Okay, can you raise your hand if you've taken an undergrad EI course? Okay, so it's more or less the people who have seen this proof. Okay, this is actually really useful information. I was actually guessing that many more of you have seen this stuff, so that's good to know, and we'll do this proof slowly. So the theorem says A star tree search with an admissible heuristic returns an optimal solution. Okay, so we do tree search like we had on that slide. We only stop when we expand the goal. That was important. And we have an admissible heuristic, so we're being optimistic. And my claim is if we do this A star thing, expand according to F plus G, to H plus G, sorry, that's going to find the optimal path to any goal, the optimal solution. Good, so let's see why. So let's say, by contradiction, that there's some suboptimal goal T that is expanded before the optimal goal T star. So there's some, optimal path to a solution, and that path will lead you to the goal T star. And, and let's say that there is some other node that is associated with maybe the same goal, maybe a different goal, but, maybe the same goal by a suboptimal path, maybe a different goal, but it's associated with some node, with some goal T, and it's a suboptimal path. And we're assuming by contradiction that this bad goal was expanded before this good one. Okay, so what we'll do is, so we're saying, look at like the optimal path between the starting state. What this is showing is our search tree. So we start here, and then we expand nodes in the search tree. So every time we when we expand a node, we add its successors in the level after, one level below. So you can picture this as this tree where the initial state is here. And, so we have some path from the initial state to the optimal goal state, T star. And what I'm drawing here is the frontier. So these are the goals that we have discovered but have not expanded yet. Okay, the nodes that we could expand. So obviously, T is on the frontier because we just decided to expand it, right? And we're saying this decision was wrong. This is not going to be consistent with the algorithm. So T is on the frontier. And also, some node on this path, it could be T star itself, it could be, the initial state, whatever, some node on this path is on the frontier, on this optimal path. Okay? So again, there is some optimal path, and we've discovered it up to some point. And I'm calling this point X, the node that we were able to reach on the optimal path. At the moment that we made a bad decision and expanded T, I call it X. Okay? So X is a node on the optimal path between the initial state and T star. So what do I know about the F value of X? And this will give me the contradiction. So let's see. So F, by definition, is the sum of G of X plus H of X. because the heuristic H is admissible, H of x is at most H star of x, the optimal cost to get from x to a goal. So we get, this is at most g of x plus H star of x. Now the crucial thing is, remember we said x is a node on the optimal path. So the cost of getting to it plus the cost of getting from it to any goal, right? T star is the optimal goal. So this would have to be the work that you would have to do to get to T star. Okay, let me repeat this. So we're saying T star is the optimal goal. X is a node on the optimal path, right? So what is the H star of x? It's basically the cost that it would cost us to travel on this path and get from x to T star, because this is the optimal path to the optimal goal. And H star is defined as like the least amount of work that you have to do to reach a goal. Does that make sense? So I'm claiming H star of x is exactly the how much work we would have to do on this path to get from x to T star. And of course there's also the work that we already did to get to x on this optimal path, that's g of x. So g of x plus H star of x is exactly the amount of work we have to do on the optimal path in order to get to T star. Right, so that would be g of T star for this optimal node that contains T star.
Could you explain the triangle again? What size and what color?
Yes. So the triangle shows the search tree in a very abstract way. So the idea is when we run tree search, we start from the initial state, and then we discover some nodes and add them to the frontier. These are the successors in the tree. And then from them, when we expand, we discover additional successors and so on. So this is the tree. Now, what are the colors? So I'm denoting the goals in blue. And we said there's some suboptimal goal T and some optimal goal T star. They're both blue. And next is some other node, this red node is some other node on the optimal path to T star. And finally, we said there's this frontier. So again, like we're thinking at the moment in time where we made the wrong decision of expanding T. And we're saying, what was the frontier at this time? Right, so A star looked at the frontier, expanded the node with the smallest f value, and that was T star. And we're saying, let's look at all of the nodes on the frontier, and the argument was one of the nodes on the optimal path has to be on the frontier. Let's call it x. Okay. Cool, so what did we get? Let's just finish this argument. So we got that this is equal to g of T star, and we said T star is a better goal than T, so the amount of work we have to do to get to it is less than g of T. Right? So by definition, we said this is a better goal. G of T star is smaller than g of T, but g of T is equal to f of T because at any goal our heuristic value is 0, and the only thing that matters is the cost it took you to get to that goal. So what we got is that f of x is strictly smaller than f of t. And that means in this moment in time, when both x and t were on the frontier, A star should have expanded x. Okay, but our assumption was that at this point in time it expanded t. So we get a contradiction.
How are you giving the heuristic value?
So the heuristic value, we're just saying, we're expanding by f. I'm not assuming anything about the heuristic. I'm just saying, by definition, this is determined by some heuristic function. And the only thing where I actually said something about the heuristic function was this transition, where I just said, the only thing is x is a node on the optimal path, and H star is not even about our particular heuristic. This is just by definition the optimal cost of getting from x to the optimal goal. Okay, so so this thing is not actually about any particular h function, and this thing is just by definition. And the only thing that we're using here is because of admissibility, h, whatever it is at most H star. Okay? Yeah.
If the condition that h is less than or equal to h star is violated just a little bit, will the optimal value change dramatically?
No. So you'll find something that's very close to the optimal value. So that can actually be proven pretty easily using a proof very similar to this one. That's a good question. What's your name?
Me?
Yeah.
Z.
Z?
Z.
Zia. Okay, cool. Yeah, I'll start asking you guys names. Hopefully I'll remember. Yeah.
Yeah, so you said that a suboptimal goal could either be a suboptimal path to the optimal goal or just a different goal altogether.
Yes.
So is H star the optimal distance? Is it the distance to the optimal goal or just to any goal? When there are multiple goals, how do you define it?
Right. So we, when we say it's optimal, we say it finds the optimal distance, the optimal path to the closest goal. So basically, any path to any goal is a valid solution, but we find the optimal solution, which is like the shortest path to the closest goal. Okay. So this is again a very important point. We're talking about search problems that could have multiple goals. But we want to find the optimal solution, which is the least amount of work to get to any goal. What's your name?
Deepak.
Deepak. Okay. So Zia and Deepak. Okay. Yeah. Name?
Ankush.
Ankush. Okay. Yeah.
Is it what happens if h of x is negative?
Right. So then, so that's a good question. I believe. I knew the answer to this years ago, so I don't remember offhand. But let's think about it offline. It's a good question. Yeah. So we're assuming the costs are non-negative.
And h of x being less than or equal to h star of x is, it's a sufficient condition, but is it also a necessary condition?
No. Yeah, we can definitely give very easy examples where we can come up with a very messed up heuristic function that magically guides you to in the right direction. Cool. Okay, so let's talk about specific heuristic functions, and this is actually something that appears in your homework 0. And I want to talk about two particular heuristic functions, to try to assess how good a state is. So the first is the heuristic function h1, and what it does is it counts the number of tiles in the wrong position. Right, so we're just looking at the board and just counting how many tiles are not in the position they should be in the goal state. The other function is h2, and this one counts the sum of Manhattan distances of the tiles from the goal state. Okay, so Manhattan distance on a grid is how many moves up, down, left, or right you have to make in order to get to the goal state. So for example, if you look at this example state, let's see how many tiles are in the wrong position. So 5 is in the wrong position, 2 is in the correct position, 6 is wrong, 1 is wrong, 3 is wrong, 7 and 8 are right, and 4 is wrong. So we have 5 tiles in the wrong position. So that's going to be h1. What's h2? So for 5, it has to move two moves to its correct position. 3 has to move 1 move. 6 has to go 1, 2, right? 1, 2. 4 has to go 1, 2, 3. Okay, so we just sum up all of these Manhattan distances, and that way we get this estimate for the sum of Manhattan distances. Cool, so here's the second poll for you guys today. Which of these heuristics is admissible? Okay, only h1, only h2, both of them, or neither one? So I'm going to open this poll on Piazza, and that's poll number 2. 10 more seconds. Okay, great. So 3/4 have the right answer, which is both H1 and H2. So would somebody like to say why H1, which is the number of misplaced tiles, why that's admissible?
It takes
Sorry, Ankush.
you can at least reduce the number of misplaced tiles by 1.
Great. Excellent. Okay, so Ankush has it exactly right. He's saying, in every move, we can reduce the number of misplaced tiles by at most 1. Right? So, and this is just counting the number of misplaced tiles. So obviously, we'd have to make at least that many moves. What about the sum of Manhattan distances? Yeah, what's your name?
Puneet. Puneet.
Puneet?
Yeah.
Uh-huh.
I mean, that's the distance at least you'll have to travel to get to the right.
Right.
Most likely you'll have to travel more.
Excellent.
At least you will have.
Excellent. Okay, so Panish is saying, again, like every move, you only move one tile. And every tile will have to travel at least that distance. If you're just allowed to travel over other tiles, you would have to travel that distance. Probably you would have to do more work. Right? So the idea behind both of these heuristics is that these are relaxed problem heuristics. Right? And the idea is that what we're doing here is removing some constraints from the problem and solving the relaxed problem. So what you can think, you can think of misplaced tiles as I'm removing the constraint that you can only move up, down, left, or right. And I'm also removing the constraint that you can only move to an unblocked tile. So that way you can just teleport every tile directly into the correct position. That would give you the number of misplaced tiles. With Manhattan distance, I'm only removing the constraint that you can't move into unblocked tiles, but I'm not removing the constraint that you can only move up, down, left, or right. Okay, so I'm removing less constraints. It's like a less relaxed problem, but still it's relaxed compared to the actual problem where we can't move into occupied positions. Okay, so thinking about these two heuristics a bit more, let's add another definition. We're going to say that a heuristic H dominates a heuristic H prime if for every node X, H of X is at least H prime of X. So notice that for admissible heuristics, this is a good thing, right? Because we're saying both of them are optimistic. They're underestimating the cost. So being larger but still lower than the cost actually says we're more accurate, okay? So when we say, H dominates H prime, this is an advantage for H. It looks like it's always bigger, but if they're both admissible, it will actually say this is more accurate than the other one in any situation. So here's poll number 3 for you guys. Let's do it quickly. What is the dominance relation between H1 and H2? H1 dominates H2, H2 dominates H1, or they're incomparable in the sense that neither one dominates the other. Ten more seconds. Excellent. 91% of you got it right. That's really great. H2 dominates H1. So would anybody like to explain why? Simple explanation? Yeah.
Every tile that's in the wrong position has a Manhattan distance of at least 1 associated with it.
Excellent.
Move it at least once.
Right, and Priya, right? Yeah, right. So Priya is saying, if we look at sum of Manhattan distances, every tile in the wrong position would have to move at least one position in order to get to its goal position, and therefore, we're counting for each such tile at least one, which is how much we're counting for it in the number of misplaced tiles. So it will always be at least as much. That's great. Okay, so let me just show you in practice how much of a difference this makes. So this table shows the number of nodes expanded by A star when you run it with these two heuristics over random 8 puzzles for various solution lengths. So these were generated at random, but in a way that is constrained so that the optimal solution has a certain length. And what you can see is that H2 makes A star do much less work than H1. Okay, so you can see this column is much, much smaller. This is the number of nodes that are expanded. That column is much smaller than the column for H1, and this really shows how important it is to have a good heuristic. Right, so dominance really gives us a very formal and clean way to say H2, both of them are admissible. So it says H2 is just better in every way than H1, but this really shows how important it is in terms of how much work it saves A star to get a really good estimate for the amount of remaining work. And H2 isn't even that great. In the homework, you have another really nice heuristic, and people have come up with more sophisticated heuristics for this problem. Okay, so the moral really is good heuristics are crucial to guide A star search. Yeah.
So is it true that if you have a better heuristic, meaning that it dominates, like example, like H2 dominates H1, then at every point H2 will take less expansion?
No. So definitely, no. So that's not true. You can come up with examples where that wouldn't be true. However, in practice, so this is sort of a practical problem, average over random instances, the effect would be pretty strong. But in general, this also ties into a previous question about, whether the conditions we talked about are necessary. So you can always come up with like crazy graphs that describe a search problem where you have a bad heuristic that, very fortunately leads you like very quickly on the optimal path. So usually these things, are not like, it's not like a universal truth. But, this is just, we have this very clean definition of dominance, and this is a practical statement. Okay, cool. So, like I said, so far we just talked about tree search, the whole lecture so far. And, what we said was, if we have an admissible heuristic, then A star tree search would actually be optimal, would find the optimal solution. Now let's think about graph search, and I want to think about whether this theorem would still hold. So remember that in graph search, the main difference from tree search was that we keep track of expanded nodes, and we never expand a node twice. So we can add the node multiple times to the frontier, but once we expanded the node, that means we're done with it, and we're never going to expand it again. So, the question is the optimality of A star under admissible heuristics preserved when we do graph search instead of tree search? And the answer is no. So let's see this example. First, I want to verify that the heuristic function here is an admissible heuristic. Right, so notice here the heuristic value is 2, and the optimal path is of length, I guess, from here, so 5. Here, the optimal path is of length 4, and we have an H value of 4. Here it's 1, and it's actually the cost is 3. Here it's 1, and the cost is 5. So this is an admissible heuristic. Now let's run A star graph search. So we start by expanding S. We get A and B. Now B has a much lower H value, so we expand B first. And then, so we're getting C with a total work so far of 3 and an H value of 1, so we get an F value of 4. Now what about A? It has an F value of 5 on our frontier. So A star would next expand C. So it expanded C, it finds the goal, right? And it finds it with a total cost of 6. So now A star goes back to the frontier and says, hey, I have this node with an F value of 5. I have this node with an F value of 6, so let's expand this node. What are the actions I can take? I can go to C. But now, do I add it to the frontier? No, because it's already been expanded. Okay, so this is where things go wrong. Right? So you're trying to go back, but you can't go back and correct, you find a better path, but you can't go back and correct the mistake that you made, basically, because C has already been expanded. So, this is sort of bad news, but notice that the heuristic function here is really weird. And one place where it's weird is giving an h value 4 to the node A. Because it's very easy to see, if you know that if your estimate here is 1, and there's like one edge with cost 1 between A and C, why would you have such a high estimate on A? Right? It's pretty clear that the work here can be at most 1. I mean, if the work here is 1, the work here should be at most 1 plus 1. Right? So this is where this heuristic function is a bit weird. It's admissible, but it's weird. So what we want to do is define a condition that would circumvent this weirdness, or would resolve this weirdness, and would get us back to being optimal. So this is this condition of consistency. So let's define by C of xy the cost of the cheapest path between x and y. Okay? So in particular, remember that before we defined h star of x, so that would be C between x and t star for the closest t star. Okay? So before, when we talked about h star, we said we just care about the distance to a goal. This function is defined between any two states and defining the cheapest path between these two states. Now, we say that if the function is consistent, if for every two nodes x and y, our estimate for x, or heuristic value for x, is at most the cost of getting from x to y plus our estimate for y. Okay, so this was again violated here because our h of a, which is 4, is larger than the cost of getting from a to c, which is 1, plus h of c, which is 1. Right, so we need h of a to be smaller than the cost of getting to c plus h of c.
It's like a triangle inequality.
Exactly. That's exactly like the triangle inequality, which I'm sort of trying to illustrate here. So it's basically saying going directly should be better than doing the work of getting to y, and then using your estimate from y to t. And there's also an optimism element here. So, the idea is if you're optimistic in estimating this cost, and you have this h value, then this edge should be at most this one plus this one, which is sort of a triangle inequality.
And then if you assume again that h of y is less than or equal to that cost, plus h of x.
Right. I mean, this could be like, the graph could be directed, so it may not be the case. Okay. So this is a directed graph. Okay, cool. So this is the definition of consistency. It's a bit confusing, so we'll talk about it for a few minutes. So here's the poll number 4 for you. What is the relation between admissibility and consistency? And by the way, for this poll and for everything actually, we're going to assume that h of t for any goal t is 0. Okay? That's important. So the question is, what's the relation between admissibility and consistency? Is it true that admissibility is stronger and implies consistency? Consistency is stronger and implies admissibility. They're equivalent, which is kind of a dumb, or not a very believable answer, or they're incomparable, which means like none of them implies the other. And if you don't know, of course, choose beats me. I'm going to open the poll. Yeah, nobody choose answer 3 because then it would make me feel really bad. By equivalent, I mean that each one of them implies the other. So they basically have the exact same notion. So it would be like a bidirectional arrow. Okay, 10 more seconds. Excellent. Okay, well, you guys are great. So 3/4 have the correct answer, which is consistent implies admissible. So would somebody like to give me the proof? Ankush.
The proof, you can prove it by induction starting from the goal node. So h of k is 0. And since h of x is less than equal to c of x1 plus h of y, so all the nodes that are neighbors of the goal, they will have h of x less than equal to the cost.
Okay.
And then you can apply induction.
Okay, yeah, so actually I have in mind a simpler proof that would just be like an assignment of like, just choosing the value of y correctly. Okay. Priya?
If you let y be the goal,
Excellent.
then h of y is 0 and the cost is the optimal cost, and so you basically just have the definition of admissible again.
Perfect. Right. So Priya is saying, the only thing we'll do is just let y be the optimal goal. So we have h of x is at most the cost of getting from x to this optimal goal, which is what we called h star of x before, plus h of the goal, which is always 0 by this point. So we get h of x is at most h star of x, which is the definition of admissibility. Okay, perfect. So this is a stronger property. And what we will want to claim is that if we impose the stronger property on the heuristic function, then we will be able to recover the optimality of A star even under graph search. So before that, let me just make another point here. Yes, I'm going to skip this poll because we just have a few minutes. I just deleted it from Piazza, but let me go over this. So we go back to the same example. Oh, actually, let me make another important point, which is why the other direction is not true. Okay, so I want to give you an example of a heuristic that is admissible but not consistent. Right. So think about like the following situation. So we have S, A, and T, and this is some very large number. And this is 1. And then this is h equals 10, h equals 1. Right? And this is h equals 10. So this is an admissible heuristic. All of these h values are smaller than like 1,000,000 or 1,000,001. But still, it's not consistent because from S, the h value of S plus the cost of getting from right. So this h value is not smaller or equal than getting from S to A plus the h value at A. So this violates consistency, even though it's very clearly admissible. Okay, good. So we don't have implication in the other direction. So this is consistency is a strictly stronger notion for heuristic functions. So let's just talk about this other point, which is, going back to our heuristic functions. I want to claim that actually both of these heuristic functions are also consistent. Okay, and the reason is that let me say this very informally. The reason is again that these heuristic functions are coming from the relaxed problem. So what's happening here, we're looking at this relaxed problem and we're basically solving it optimally. So what you can do is you can say, okay, in the relaxed problem, the triangle inequality actually holds. It's always going to be easier to go like in a direct path from one state to another compared to going like through some other state and then taking the path from that state to the goal. So what we would have is, whatever the cost of the solution of x in a relaxed problem would be at most, let's call it C prime of xy, where C prime is the cost in a relaxed problem, plus, whatever it costs us to solve the problem from y. But because we're again in a relaxed problem, this is at most the actual cost in the real problem of getting from x to y plus h of y. Oops. Yeah. Okay, you can see this? So, let me try to turn this on and off. Okay, but the point is, basically it's the same kind of relaxed problem argument. You can also say, because we derive these heuristics from a relaxed problem, that would also imply consistency. Okay, so this is a very informal argument. You can think about it a bit at home. But both of these heuristics are consistent. And actually what I'm saying here is that a good heuristic for designing consistent heuristics is designing admissible heuristics. And the reason is that most natural heuristics that you would be able to think about actually come from relaxed problems and also end up being consistent. So it's actually pretty hard for natural problems to think of heuristics that are admissible but not consistent. We saw that there are such examples, but for natural heuristics and natural problems, usually it wouldn't happen. Okay, so this is saying, actually imposing consistency is not such a big deal. It's not like a big restriction compared to just admissibility. Okay, so now we have one more slide, and I'm deliberating whether to do it now or in the next lecture, and I've decided to do it in the next lecture. So that's all for today.